Hello friends, I welcome you again to another video. In our last video, we said something about carbon. If you all remember, I introduced carbon and I started by telling you how important carbon is. That even deep down there in our DNA, if you talk about the DNA basis, you will see the presence of carbon embedded in our DNA basis. Our skin, every part of us, has carbon in it. Although other elements are important, like I mentioned to you, that the human hair here is made up of sulfur. So those of you that keep distorting your hair, you place it in a very terrible heater, and you see your hair waxy, coily, and you come out, wow, my hair is curly. No, you're actually distorting the disulfide bridges down there in your human hair. So take note. But today we're not looking at sulfur, we're looking at carbon. Carbon is so important that in inorganic and organic compounds, you see carbon as a major element. Carbon, I said, can exist in elemental form, or you can see it in combination with other compounds in natural state. For example, look at carbon I mentioned dolomite. Here, dolomite, our magnesium trioxocarbonate 4, MgCO3. What did you see as the central atom? Carbon here, very important. Even carbon is also present in your limestone. Yeah, your limestone. Remember, CaCO3, CaCO3, calcium trioxocarbonate 4. Look at this. Carbon is also a major compound. And remember, I told you this is chalk but different from blackboard chalk, which is calcium tetraoxosulfate 6. Good. So you can see carbon not only in elemental form, but also in combination with what? Compounds such as this. These are inorganic compounds. Or in organic form also, you can see your carbon. For example, in your methane, in your ethane, your propane, what do you see? Carbon as a major compound. So, and that is why they said organic chemistry is the chemistry of carbon compound, because carbon plays a major role in it. Even if you want to name organic compounds, what do? The parent chain. You look at the longest continuous carbon skeleton, isn't it? Yeah, and that is why carbon is important. So, before we go into an in-depth study in carbon, we must look at these elements in its entirety. First, what is the atomic number for carbon? Yes. What is it? Yeah, 6. Very good. You got that right. If you said 6. Okay. Now, carbon is 6. That means the electronic configuration of carbon is what? Look at the electronic configuration of carbon. Is 1s2, 2s2, and 2p2. Yeah, this is the electronic configuration of carbon. And remember, I have S, S, and P. I believe you know what they are. They are called orbitals. We have 4 major kinds. We have the S, the P, the D, and the F. And what do they stand for? This means sharp. P means principal. D means diffused. And of course, our F means fundamental. I'm not going in depth into that. There will be a time when we get to the organic compounds, the part of that where you discuss organic orbitals in theory. We're going to look at that. But right now, we have all this. This is the electronic configuration for carbon. And if you look at this, look at the P, the outermost, has 2. Now, with this, it is assumed that carbon is supposed to have a valency of 2, plus 2, right? Because it has 2, the outermost, it has 2. But carbon does not exist with this valency of plus 2. Instead, it has a plus 4. So how come? How is it that carbon, instead of having 2 being the outermost, the one in the outermost shell, instead of having plus 2, carbon has plus 4 as its valency? This is as a result of the phenomenon which we refer to as hybridization. Now, what is hybridization in carbon? Hybridization is the mixing of orbitals at the excited state of carbon. This is hybridization in carbon. The mixing of orbitals at the excited state of carbon. You know, we have two major states. We have the ground state and we have the excited state. At the ground state, the element is not reacting. At the excited state, that element has started reacting with other elements. So when you have this, the mixing of orbitals, when carbon starts mixing with other elements at its excited state, that phenomenon is what we refer to as hybridization. And that is what gives carbon the valency of +4 instead of +2. So right now, let's discuss the three major hybridization patterns that we have. Remember, we have sp3, we have sp2, and we say we have sp, hybridized orbitals. You were taught that sp3, you see it in alkanes. That's your saturated compounds. Saturated, they have single bonds. sp2, you have it in alkenes, while sp, you have it in alkynes. These are both unsaturated compounds. Now, let me explain, which most books will not do. How did we come about the sp3 as the hybridized orbital in alkane? Let's pick up the first alkane. That's methane. Now, methane has carbon and 4 hydrogen atoms. So let's see our carbon now. Remember, still atomic number of 6. The electronic configuration is 1s2, 2s2, and 2p2. And that means if I'm going to draw my orbital diagram, I have 1s2, I have 2s2, and for the p, I'm going to draw 3. I will explain much later. We have the 2px, the 2py, and the 2pz. Now, this is said to be the ground state. The element is not reacting. This is just carbon at the ground state. Now, 1s2, I feel this. 2s2, 2 electrons, but the p, I will feel it singly. Remember what Hund's rule states. So I'm going to feel this. These are degenerate orbitals. So I am feeling them singly. This is the ground state electronic configuration, an orbital diagram for carbon. But look at now, carbon wants to start reacting, the excited state. Remember, I told you the excited state means that element has started reacting with other elements, just as carbon reacting with 4 different atoms of hydrogen. So at the excited state, something is going to happen. Follow me here. I have my 1s2, this is the 2s2, this is my 2px, the 2py, and 2pz. Now at the excited states, I have this. What you will see is a promotion of electrons. Electrons will be promoted from the closest orbital to the empty orbital. You see, it's quite unfair. This guy has an electron. These even have pairs of electrons. But this guy here is empty. So it will be quite unfair to carry out this reaction with the empty orbital. So the first thing that will happen is a nice 2s2 will transfer 1. It will look at it, gosh, I have 2, I can give out 1. And that is what it does. There will be a promotion of one of these electrons into the empty orbital. So I will have just one here now. I will have this. Now this is the one that has been transferred. This is the electron transferred from the closest orbital. Now after this, remember this is the excited state. How many hydrogens reacting? 4 different hydrogen atoms. So each of them will go to the unpaired orbital. So 1 hydrogen will come here, 1 hydrogen will come here, 1 hydrogen will come here, and the 4th hydrogen will come here. That is at the end of excitation. So look at this now. At the end of this orbital formation, how many orbitals are involved? 1, 2, 3, 4. Yes, 4 orbitals. How many s orbitals? 1 s orbital involved. How many p orbitals? 3 p orbitals involved in that hybridization. And that is why the hybridization of methane is sp3. I trust you understand that now. Yeah. You see how they got the sp3? As easy as ABC. Now the same thing will happen for alkanes. And that means for alkanes, I will have 1 s orbital and 2 p orbitals involved in the hybridization. While in your alkynes, I will have 1 s orbital and 1 p orbital involved in the hybridization. And please, once this is done, look at this. Once this is done, the excitation will lead to the formation of bonds. That is why if I have this, this is my methane, CH4. This is my methane. Now, a carbon and a carbon in alkane, what you see is just a sigma bond. This is a sigma bond. A sigma bond. If it were a double bond, what you see is a pi bond and a sigma bond. But if it were an alkyne, what you see is a pi bond above, a pi bond below, and a sigma bond. I trust you understand. So for alkanes, for saturated compounds, between the carbon-carbon bond, I have a sigma bond. For the alkene, between a carbon double bond, carbon bond, I have 1 pi bond and 1 sigma bond. For the alkynes, between the carbon triple bond, carbon bond, I have 2 pi bonds and 1 sigma bond. I trust you understand the hybridization pattern in carbon. Now I told you carbon is very important. Studying carbon, we need to look at crevices, every aspect of carbon. You must have perfect knowledge of carbon before we go into the allotropic forms, because there are 2 major allotropes. We have the crystalline and the amorphous. The amorphous is the shapeless allotrope. Yeah, the word amorphous means shapeless. So we have the crystalline and we have the amorphous allotrope of carbon. Now in our next video, what I'm going to do is I will lay emphasis on these categories of allotropes, the allotropic forms. That's the crystalline and the amorphous. Now remember that the crystalline allotrope involves diamond, graphite, and the fullerenes. Yeah, is this the first time you've heard that? The fullerenes. Yeah, carbon 60, C60 and above. 60 carbon atoms and above. Those are the fullerenes. Although the usefulness of this is still being studied, but remember, it is not just diamond and graphite. We still have the fullerenes. Why the amorphous forms in coal, they include coal, lamp black, animal charcoal, sugar charcoal, and so on. All these we'll discuss in our next video. Please remember, for these videos to keep coming, go to our YouTube page and click on the subscribe button. It's the Simplifier one. You can still find us on Instagram and on Facebook with the same name, the Simplifier one. Thank you, and I'll see you in the next video.